Since the average power comes in two forms, real power and reactive power, we need some method to express them as a single quantity. And in electrical engineering technologies, we express this single quantity using the concept of complex power, often represented in a graphical technique called the power triangle. So complex power is the vector sum of the real and the reactive power. So we would say that complex power, represented by the capital letter S, is equal to the combination of the real power, P, plus the reactive power. Now, because reactive power is due to reactive components, we're still going to use that component J in front of it. This indicates that reactive power is not absorbed or consumed by the load, right? It's not converted into heat. This is. We have to differentiate them. We go back to that J operator. This is a vector, right? It's got a real and an imaginary component to it, so technically S is a vector, P plus JQ. S equals P plus JQ. It is measured in a unit that is different than either power, which was in watts, or reactive power, which was in VARs. And its unit is called the volt amp. Capital V, capital A. Complex power. The magnitude of complex power, S, is just equal to the magnitude of this vector, P plus JQ. It's going to be the square root of P squared plus Q squared. So again, in terms of units, apparent power is the same as average or reactive power, but to distinguish it from either of these, we tend to use the units of volt amps reactive. And I've summarized those for you in a chart here. So we've got power quantities and their associated units. We now know that there are three types of power. There's apparent power, S, measured in volt amps, capital VA. There is average or real power, which is P. It's measured in units of watts, capital W. And there's Q, reactive power, volt amps reactive or volt amp reactive, and it's the VAR. So if somebody says, I have 50 volt amps, they're talking about apparent power, which is the combination of the two. If somebody is talking about watts, they're talking about real power. And if they're talking about VARs, they're talking about reactive power. We can represent power as a vector in the complex plane, right? It's got a vector of magnitude S, like we showed there, that makes an angle of theta with the real axis. It's going to result in one of two diagrams. In these diagrams, the projection of S onto the real axis has a length of P and corresponds to real power. So if we have the apparent power vector and we were to figure out how much of it lied on the x-plane, well, we'd use trigonometry. We'd use our trigonometric identities, SOHCAHTOA, and we'd find out that P equals VI cosine of theta, right? Power is the real projection of the apparent power. Real power is the projection of apparent power onto the x-axis. The projection of S onto the imaginary axis has length Q and corresponds to reactive power, VI sine of theta. The angle theta here is the same as the phase difference between the voltage and current. So the angle measured between real power and apparent power is always the same as the phase difference between the voltage and the current and the load. It's still that power factor angle that we were talking about. When Q and S are in the first quadrant, the power factor is said to be lagging, or current is lagging the voltage. When QRS are in the fourth quadrant, the power factor is said to be leading. Current is leading the voltage. When we consider the entire system, the different power factors of individual loads will combine together into one aggregate power factor for the set of loads, and that's kind of an advanced topic that we will talk about later. So if we were kind of interested in what are some of the sources of reactive power, what things in the system produce reactive power? Well, primarily it comes from generators. Generators can supply reactive power. Capacitors, interestingly, are thought of as supplies of reactive power, and then lightly loaded transmission lines supply reactive power. So if I have transmission lines that aren't carrying a lot of current in them, they actually will supply reactive power. Sinks of reactive power, well, a generator can alternatively be run as a reactive power sink. Inductors are the primary sink of reactive power in the system. Transformers are probably the second most common sink of reactive power. Heavily loaded transmission lines and most customer loads, which are pumps and things like that, are sinks of reactive power. Well, why do we even talk about this reactive power? Why don't we just leave it decomposed into its P and its Q components? Well, the influence of this apparent power, we really can't underestimate it. Overall, electric utilities have to engineer systems such that the generator is connected to a system with a power factor between 1 and 0.8 lagging to supply, meaning that the system looks inductive. To supply the needed VARs to the system, utilities will often put capacitors on the system to balance out L, or they'll adjust the AC generator's field voltage, which has the effect, which we'll learn about later, of supplying reactive power. If the utility fails to balance the VAR requirements of the load, the voltage and the frequency in the circuit will be changed to enforce the law of conservation of energy, and failure to maintain a reactive power balance will typically manifest as a voltage variation on the system. In contrast, failure to provide real power typically manifests as a frequency variation. We'll learn about that in generators. Low power factors, meaning that we're having lots of Q, they're undesirable from a system perspective because the oscillations in current that result from the delivery of reactive power are real. We're not changing energy, but current does flow in the system, proportional to S here. S is V times I. Current, total current flowing in a system is determined by S. Not by P alone, not by Q alone, but by S. So what happens there? Since the current is increased, there's going to be physical heating of resistive elements, right? We know that there's Joule heating in resistive components, the I squared R heating. The bigger Q gets, let's just draw a bigger Q here real fast. The bigger Q gets, the larger the magnitude of S, the bigger I has to be for a fixed voltage. The bigger I is, the more current is flowing. That's what big I means, right? The big current is flowing. And what happens then is that the physical system sees more current flow. Bigger conductors are necessary, bigger transformers are necessary, all that thing. So there are real consequences of this. Even though we're not using up energy, more current flows, and then we actually do end up using more energy because our transmission lines burn up more energy in the form of heat. A very interesting kind of cascading effect. Additionally, customers only pay for real power and not the infrastructure needed, not the big cables and everything needed to supply Q, although that is not true for industrial customers. They do pay for facility fees to supply Q. And so the electric company can't recoup a lot of that because they can't charge residential customers for Qs. So a lot of times what they'll do is they'll perform what's called Var Compensation or power factor correction, in which they'll place capacitors on the system near the load to cancel out the in this case the inductive effects. And what that does is that minimizes the distance that the reactive power has to flow through transmission and distribution lines, reducing the Joule heating of the transformers, of the power lines and such things. So let's do a quick example of a complex power calculation. We've got an electrical load. It's operating at a 240 volt RMS supply. The load is going to be absorbing an average power of 8 kilowatts, and it's got a lagging power factor of 0.8. Let's go ahead and calculate the complex power of the load, and then also use our results to find the impedance of the load. So I've drawn a power factor for a power factor with a lagging load. Because it's lagging, we know that the load is inductive, and therefore the power triangle has to fall in the first quadrant, meaning that we draw it real power on the real axis and then reactive power pointing up. So this is a general power triangle. From this power triangle, we can see that P equals S times it's actually the magnitude of S times the cosine of theta, right? We could do some division there, and we find that the magnitude of S is equal to P over the cosine of theta. And similarly, we could say that Q is equal to the magnitude of S sine of theta, and we're just using the triangle relationships to show this. We were told something about theta. We were told that the cosine of theta equals 0.8. Where did that come from? Well, we were told that it was 0.8. Power factor was 0.8. And remember, cosine of theta is 0.8. So what we can then do is determine, we would take the inverse cosine of 0.8. We could use that result. We find out that the sine of theta is 0.6. I encourage you to try that with your calculators at home. So now what we can do is we can just plug these numbers into here, right? So we were told that the system draws 8 kilowatts. It's a kilowatt, so that's a power, real power. So if we want to know apparent power, we divide 8 kilowatts by the power factor. Magnitude of S, the apparent power, is equal to 8 kilowatts divided by the sine of the power factor angle, which the cosine of the power factor angle, which in this case is just 0.8. So the magnitude of S is equal to 10 kilovolt amps. All right. What I can then do is I can calculate the reactive power based on that relationship. I've got 10 kilovolt amps times the sine of theta. Sine of theta in this case is 0.6, so I get Q equals 10 kVA times 0.6, so 6 kVA. Oh, sorry, not 6 kVA. Somebody hopefully caught that. 6 kilovar. It's reactive power, so 6 kilovar. So we've got the magnitude of S is 10 kilovolt amps. The magnitude of P is 8 kilowatts. The magnitude of Q is 6 kilovar. So if we wanted to, we could plug these into the triangle. We could say that this is 8 kilowatts here, and then this value here is 6 kilowatts. And that shows us that we could represent S as equal to 8 plus J6 kVA, right? And we know the magnitude of this from the Pythagorean theorem is the square root of 8 squared plus 6 squared. So the square root of 64 plus 36, the square root of 100, 10, right? So that kind of shows the consistency between the couple different measurements there that we've been using. So you'll notice we wanted to calculate the impedance of the load too. That was the next step. So how do we calculate the impedance of the load now that we know the complex power of the load? So to do that, we're going to calculate load current. So we can use either the average power formula or the average reactive power formula either average real power or average reactive power formula to calculate current. It doesn't matter which one. I'm going to just choose the average power. I'm going to write that the average power is equal to, remember, it's the RMS voltage, RMS current, cosine of theta. Sorry guys, my magic board is not happy with me today. Having a little trouble on these far margins. So cosine of theta, right? If I had wanted to do it with Q average, I just would have written IRMS V RMS sine theta, right? The math would have worked out a little bit differently, but we would have ended up with the same result. We saw that we had 8 kilowatts or 8,000 watts. We don't know IRMS. VRMS was given to us as 240 volts in the problem statement. And then cosine of theta, that was given to us as the power factor, 0.8. We do all that math, we get the RMS current is 41.67 amps. Okay, so next what we would have to do is calculate the angle of the load impedance. It's the same as the power factor angle. So I kind of had asked you to do this a second ago. I'm going to go ahead and give you the answer. Theta is equal to the inverse cosine, or the arc cosine, of the power factor, which was 0.8. And that gives us a value of 36.87 degrees, right? Be careful when you do this. Your calculator needs to be in either degree or radian mode. You could come up with the right answer. So note that we know the result of the inverse cosine results is going to be a positive angle because we were told that the load is lagging. Had the load been specified as leading, we would have to add a negative value to that result. Right? So we don't have to change it in this case because we're in the first quadrant. But if we had been in the third or the fourth quadrant, we needed to toss a negative sign in front of that. So the magnitude of the load impedance can be calculated using the RMS values for voltage and current. We get the magnitude of Z is just equal to VRMS over RMS. Sorry, VRMS over IRMS. So that's 240 volts divided by 41.67. So that gives us a value of 5.76. But it's a complex load. We know that it's an angle of 36.87. From our previous calculation, since the angle between the voltage and the current has to be the same as the angle between the real and the reactive power, or sorry, the real power and the apparent power. So that is basically a complete calculation of real and reactive power using phasor notation there. So kind of handy.